Okay, so what we're going to be looking at here is another lab demo, and this one's going to be the tangent galvanometer. We have a set up version of this in the back of the room here, in the back of the lab, and what we're going to be doing with this is we're going to be looking at a compass needle, the Earth's B field, a little bit of idea with vectors and how we can add those vectorially with the head-tail method together, and then kind of a hodgepodge patched together way that I set all of this up. So let's run it back to the lab and see what we got going on for this tangent galvanometer. Okay, so this is our setup. Here, let's move this real quick. Oh, going through space. So everything's a little bit weird here. This itself is the tangent galvanometer, this piece right here. The way it's supposed to work is you're supposed to put a D-cell battery into this blue holder, and that's supposed to supply the current, which runs through, this little setup with a little switch here, and then it goes through this looping coil to create a B field. And we know that, the coil is wrapped this way, so if I use the right-hand rule, I'll see the direction of the B field. The issue is that I don't have a D-cell battery, so what did I do? Well, I've got this Vernier circuit board 2, and I hooked up two AA batteries. AA's and single A's, or AA's and D cells actually have the same voltage of 1.5 volts across them. I just want a little bit more oomph so we could see it. So I put in two batteries here. I went from the positive edge terminal and I brought it out, and then we're going to need our current later. So I passed it through this Vernier current probe in series, because that's how you set up currents. Clipped it up to the positive end of the D-cell battery, rolled it over to the negative end, because that's how these are set up in the battery holder itself, and then rolled it to my negative terminal here so that we come home. So that's the whole setup of this. So we set up the positive end, it runs through everything, kicks out the negative end, comes home, we're done. Now what's actually going to happen here, and we'll just do a quick little show of this, is in the tangent galvanometer itself, we put a compass. And the reason being is that we know that once the current is running through those coils, if we do the right-hand rule, it's going to produce a B field. It's going to produce a magnetic field here. And the way we have this set up is actually perpendicular to the Earth's magnetic field. And here's why. So our compass inside the tangent galvanometer right now, it's pointing along the Earth's B field. So it's pointing north, okay? So like this is north. We'll call that north there, right? Okay, we'll do this. We'll redraw this. So it's pointing north. Now what we're going to do is, because our looping system, our loops here, are set up perpendicular, 90 degrees to the Earth's magnetic field, so this is like the B field of the Earth here pointing north. What's going to happen is the tangent galvanometer, when it creates a B field in the coils, it's going to point like this. So this is going to be the B field from the coils. And we're adding them together, if you recall, using the head-tail method, because these B fields, they're vectors, which means that's how we have to add them together. And what's going to happen is when we add these B fields together, we're going to get a new net B field that's going to be like this. This is the total B field from the addition of the Earth's magnetic field and the coil's magnetic fields. So we're going to get some kick out to do that. And this angle here will be some angle reading from the compass itself. So we should see the compass deflect by some amount whenever we turn this ghillie coil on. So let's run back to the lab, and then let's check this out. So when we initially turn these on, there's three settings on the tangent galvanometer that allow us to turn it so it's set for 100 loops on the coil, 200 loops on the coil, or 400 loops on the coil. And when we do this, if we take a look at the compass here, we're going to see it deflect. And it should deflect based on the right-hand rule. That red arrow on the right, it should deflect towards us because the B field is going to be coming out into the room, like past me, and the north direction in the room is actually forward. So north is this way, the B field from the coil is going to be this way, so we should get a deflection coming out into the room, kind of facing us somewhere. So when we turn this on, in 3, 2, 1, look at that deflection. We got a huge deflection right off the bat. If I'm looking at it, it's about 55 degrees, give or take, by the compass. And if I turn it to 200, we get more deflection because there's more turns there. More B field can be generated. And if we switch to 400, we get an even larger deflection once again. So let's turn this sucker off before I drain all the batteries. So boom, boom, and then boom. Look at that, we've aligned back to Earth's magnetic field. And let's break down exactly how we can kind of figure out what's going on here in this setup. So let's bring this big screen. So Earth's magnetic field, it's a number, right? It is some constant. And it's actually going to be a bigger number than the coil's magnetic field, but the coils are so close that they're going to have more of an influence than the Earth's magnetic field here. So that's why this is actually a larger value in terms of setting everything up. Now, while the Earth's B field is just a number, what is the B field of the coil? How can we figure that out? Well, if we recall, if we go back to Biot-Savart, in Biot-Savart, we know that for a circular loop of wire, the magnetic field due to it is equal to mu naught I phi over 4r. And in our case right here, oh, oops, did I say 4r? I meant 4 pi r. In our case right here, what's going to occur is, one, we're going through an entire loop of coil, so our angle here is going to be 2 pi, and our current here, it's actually going to be many currents, because I don't just have one loop of coil, I've got 1, 2, 3, 4, 5, 6, 7, 8, all the way to 100, and then when I flip the switch, 200, and then 400. So this is going to be some number n times that current passing through the coil. So what we're actually going to see for the B field of the coil itself here, that's going to be equal to mu naught I n, and then we're going to see the pi's are going to divide out, and the 2 and the 4 are going to reduce. So we get 2 mu naught I n over 2r, and that's going to be the B field of the coil here. So if we want to actually look and say like, hey, look, there's a deflection here. Well, this is a nice right triangle. And I know that the Earth's is a constant, the Earth's B field's a constant, and I know the coil's B field. I can actually start looking at this triangle and using SOHCAHTOA with a opposite side, an adjacent side, and a hypotenuse to start analyzing this in terms of the angle of deflection here. And what we can quickly see is that with an opposite side known, because that opposite side is the coil's magnetic field, and with an adjacent side known, the B field from the Earth, it's just some number, whatever it is, we can actually say here that the tangent of angle theta, so the deflection angle that we see here, is equal to the coil's B field divided by the B field of the Earth. And since we know the coil's B field, we can say that this is all equal to mu naught I n over 2r times the B field of Earth in the denominator there. So that is equal to our deflection angle. And what we can do with this is, if we happened to know what the Earth's B field is, we could solve for the current going through these wires. We could actually say that the current I, what we're solving for, is equal to 2r, the B field of the Earth, some constant, times the tangent of theta, divided by mu naught, which is a constant, times n, where this is either 100 or 200 or 400 loops, because that's how this device was made. So if we wanted to, we could go and solve for the currents here. But I don't know off the top of my head what the B field of Earth is. Maybe I could look it up and then I could do this. But what I do have access to right now, if you recall in the lab, is I put a current probe into this system. So let's actually try to figure out what the B field of Earth is like this. Instead of solving for I, let's go ahead and solve for B. I know then that the B field of Earth, if I kind of rewrite the equation above, this is going to be equal to mu naught I n over 2r times the tangent of theta. So let's take a look at this equation where our mu naught is the constant, I is the amount of current which we are going to have to measure. So here, let's label some of this. So this is a constant. We can measure this. This is either 100, 200, or 400 depending on the setting of the system. That's the number 2. This is a measured value, r, and then tangent of theta, well, we can measure this angle off the compass. Okay? So let's go ahead and try this out and see what we get here. So let's run back to the lab real quick and see what's going to happen. Okay, so back in the lab here, what do we need to measure? We need to measure the current, which we can bump up a vernier LabQuest for that. So let's pull up LabQuest here. We've got a current probe hooked up just like before. And it looks like this is crashing, so let's pause for a second. Okay, we're back in business. So we've got a current collection thing here, so we'll be able to get that. We know N is going to be 100, 200, or 400. We know 2. Let's get R real quick. Okay, so I've got a kind of weird ruler here from Coach Bay. It's actually the back side of her keyboard. But if we do this, and we measure this, I'm going from the acrylic upward, and there's no way you can see that. I'm just kind of covering things up here. But when I measure this, I get, looks like 4.5 centimeters. Okay, let's just write that one down, or else I'm going to forget that one. Let's just say R equals 4.5 centimeters, or that would be 0.0045 meters. And I could probably be more precise with that, but it is what it is. So now let's just turn this on at 100, and let's see what we get here. In terms of the deflection, because we know that 200 and 400, like, we're going to get different values for everything, and the currents are going to change too, because as you have more loops, you have more copper coils, and that means a slightly bit more resistance due to the extra length. So we know this current's going to change slightly as N changes. So let's just run this once and see what we get. So let's just do it for 100 and figure out whatever the current is there, and let's measure an angle. So let's pull up the graphical analysis and let's see what we got. So let's run the data and then turn this to 100 and off, and it looks like our data did not record properly. So let's see what's going on. Oh, there it is. Okay, so it was at 100 and then off. Took it a second to bring up. So let's see what we got here. What's our current? 0.0206. There's a weird spike when I turned it off. So let's go with that. Let's go with the current being 0.0206 for that. So current here, let's see, where's our current? Current equals 0.0206 amps. N equals 100 here, and then, oh, you know what we didn't get? We didn't get this whenever we did that. We didn't get the deflection angle, which I think before it was like 55 when we did this. So let's just check it again. I'm getting something between 50 and 55 here. Let's just say 52. It's kind of hard to tell. I'm gonna make it my estimation on my angle that it's offset by theta equals 52 degrees. Okay, so I've got my theta, so that's good. I've got R, so that's good. I've got current, so that's good, and I've got N, so that's good. And then mu naught is a constant, so we can look that up because I can never remember that one off the top of my head. Magnetic permeability of free space. And it is 1.26 times 10 to the minus 6th. 1.26 times 10 to the minus 6th. Okay, so let's see if we put all this together, what we're going to get here. Boop-a-doo-boo. Let's see, let's write this all out because I've got everything all over this page. So let's work out our math over here. The B field of the Earth, according to our calculations, will be 1.26 times 10 to the minus 6th multiplied by our current, 0.0206, multiplied by the number of turns, 100, divided by 2, divided by 0.0045 meters. And we want meters here because those are our SI units. We don't want the centimeters that we actually measured in, and then divided by the tangent of 52 degrees. And remember, the tangent of 52 degrees is just some number here that we can get. So let's chug this all into a calculator, see what we get, and then actually like compare that to what the Earth's B field is. And I don't remember off the top of my head what the Earth's B field is, so this will be a surprise to all of us. So 1.26 times 10 to the minus 6th times 0.0206 times 100. So right now I've got 2.59 times 10 to the minus 6 if you're following along. And then divide by 2, divide by 0.0045, it's going to make this bigger. And then divided by, and then watch your parentheses, the tangent of 52 degrees. And I am in degrees here, so this should work. And we get, as our Earth B field, according to our little lab we did here, of 2.25 times 10 to the minus 4 Tesla, because that's the units of B field. And I think that's actually pretty close. The only thing I remember about the Earth's B field is I think it's in times 10 to the minus 4. So strengths of Earth's magnetic field. And YouTube tells me that it is about 0.3 times 10 to the minus 4. So we're a little bit large here. We're a little bit large. And that could have probably been factored in either due to one of these R values or one of these tangent values. This compass we used wasn't exactly perfect, but the main thing we see here is that we are in the same order of magnitude. And whenever you're doing quick little labs and stuff like this where we're just kind of like quickly measuring things, being in the same order of magnitude is a great place to start. You know that you are doing something right in that lab. Anything getting closer to that point is simply a matter of getting more precise instrumentation and seeing what else we could do with that. So maybe in this case, maybe the compass isn't exactly placed in the center of the loop. Or maybe the compass is a little too big for the loop and it's getting some outside effect. Maybe I don't have it lined perfectly north so that, our tangent angle is slightly off. Like, I don't know. But we got the same order of magnitude, which is great for us. I'm going to call that a win on our end because, it is a win on our end. So, yeah. But that right there, that's a tangent galvanometer. They've been in use for, nearly about 200 years now. Around 1820 they came up and started being used a lot. So that's a quick way that we can actually get the Earth's B field if we wanted to measure that or something get close to it. And if you happen to know the Earth's B field, you can get currents of lots of things as well. Okay, so that is the tangent galvanometer. Hope you enjoyed this little demo here. It was something a little different. And until next time, adios, and y'all take it easy.